Hi there, welcome to a new unit of IB Physics. This is Fields and Forces. Specifically today I'm going to be talking about gravitational force and field. Now this diagram, and it is a kind of a diagram of the model of what a gravitational field is. A gravitational field is just a useful tool, a model, which is used to explain the influence of a massive body as they extend into the space around it, producing forces on the bodies. Okay, so this is the reason why we're attracted to the centre of planet Earth. This is why the moon orbits around the Earth and the Earth around the sun, because of the forces which are involved. Okay. So because this is a model, and it's quite, I guess, theoretical, but it explains things quite well, we can imagine it however we want to imagine it. I like to imagine it as the inexplicable force between Catwoman and Batman. Now, the interesting thing here is that if we understand cartoons anyway, there is an inexplicable attraction between the two of them. To explain the attraction is very, very difficult, as with gravitational forces and fields. What's actually going on is incredibly complicated and misunderstood, and I'm not even going to try and explain that in any way, because it touches on some fairly advanced physics. Well, we have to accept that there is an attraction to Catwoman by Batman, and there's also an equal and opposite attraction of Catwoman to Batman. That's how I think about things. Obviously, there is not a law named after me. Newton was the first person who came up with this, and he developed Newton's law of universal gravitation. He said, every particle of matter in the universe attracts every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. And it was hypothesized or thought that this had something to do with an apple falling on Newton's head. However, we don't consider that, or we don't really use that as Newton's law of universal gravitation. We think of it as a simple formula. Okay. So Newton's law of gravitation comes in a formula which can be written as force equals gravitational constant times the mass of one object multiplied by the mass of the other object divided by the distance between the two particles. So G is Newton's constant of universal gravitation. It has a value of 6.67 times 10 to the minus 11. And looking at the units there, we'll notice that meters squared, so the value of R must be recorded in meters, and the values of the two masses must be recorded in kilograms. That's the crux of it, really. It's a law which helps explain this mysterious attraction. So let's think about some questions here. I've got 3 questions here, and we'll give you a moment to answer this. So if you can press pause and step away. Now you've completed those questions. And we'll go through some answers quite quickly. The gravitational force between a person who's about 80 kilograms, a little bit like me on a good day, and someone who's 60 kilograms, 100 meters away, is going to be 2.91 times 10 to the minus 8 newtons. It's a very small value when we're considering objects which have a relatively small mass. When we crank up the mass a little bit more, so here I'm looking at an object of a mass of 2 times 10 to the 30 kilograms, which is loosely the mass of the sun as it happens. Here, although the mass is still great, the distance of which the sun is away from us means that the force is still relatively small, 0.399 newtons on a person who's 80 kilograms. So this is something they're not overly going to notice. But we can see if we increase the mass dramatically, it has a dramatic effect. Now, what assumptions have you made in each of these questions? I didn't mention any assumptions that were made when I was just talking about it, but this is a moment just to highlight this point. What you've assumed in both these cases is that these are point masses. Okay, an 80 kilogram person, we're assuming that the mass is focused at their centre of mass. The object of mass 2 times 10 to the 30 kilograms, we're assuming it's equivalent to a point mass at the centre of that object. As it happens, that assumption works very, very effectively for spherical objects with a constant density, and for objects which aren't spherical, more often than not we wouldn't have to worry about that. That's why the assumption is acceptable. So that's your introduction to gravitational field and forces.